Okay, in this lecture, we're going to be going over when and how to utilize a t-distribution. So a t-distribution, you utilize a t-distribution when you don't know the standard deviation of the population. Often, well, not very often will you actually know the standard deviation or the mean of the population. So a t-distribution is very useful. Okay, so to determine the confidence level when the population standard deviation is unknown, we use the t-distribution. The formula is the mean of the sample plus or minus the t-value multiplied by the standard deviation of the sample divided by the number, the square root of the number in the sample. Number of observations. For example, the dean of the business college wants to estimate the mean number of hours full-time students work paying jobs each week. He randomly selects 30 students and asks them how many hours they worked last week. He calculates the sample mean, but he is unlikely he would know the population standard deviation required to be able to utilize the z-score. So we don't know the sample mean here, and we don't know the sample standard deviation. But if we did know that, from what the dean calculated, we could calculate this information. Okay, so the t-distribution is a continuous distribution. It's mound shape and symmetrical, so just like the z-distribution, it's very similar. However, it's flatter and more spread out than a standard normal distribution, and the reason for that is because it is accounting, it's giving more of a buffer for, the variance. It's being more conservative, if you will. The z-distribution, you can be a little bit more precise because you know one of the population parameters. If you know one of the population parameters, you have the capacity to be more precise. But since we know none of the population parameters and we're trying to build everything just off of the standard, or just off of the sample statistics, we have to be a little bit more conservative in our interpretation. And also there's a family of t-distributions based on the number of degrees of freedom. Okay, so when finding a value of t, the first thing that we need to do is assume that the population is normal, or rather test to ensure that the population or that the sample is normally distributed. Okay, so in the back of your book you can use Appendix B.5 and move across the columns, or if you want to, I actually gave you guys a PDF of this, and this is on your this is on Canvas. So I'm going to show you guys how to use this. So in the next example, we want to use the 95% confidence level, and so we need to move to that confidence level, and then we're going to calculate the degrees of freedom. And what we're doing is right here, we are determining, we want to be sure that the, remember when we take a statistic and we use it as a parameter, it's called a point estimate. So essentially, we want to have confidence that our point estimate is accurate. And so we have a point estimate, we have no population parameters, and we want to be sure that it's accurate. Okay, so let's take an example. Okay, so first, before we take an example, to calculate the numbers of degrees of freedom, the degrees of freedom is the number in the observation, or the numbers in the sample, numbers observed, minus 1. Okay, so degrees of freedom is n minus 1. So if you have 10 individuals in your sample, okay, what you do is you come down here and you find degrees of freedom 10, but degrees of freedom is not 10, it's 10 minus 1, so degrees of freedom is 9, and then you have the confidence interval right up here, so it's 95 and 9, so the degrees of freedom is 2.262. if we had 11 in our sample, so then the degrees of freedom would be 10, and 95% confidence interval would be 2.28. Okay? So, the level of confidence, for example, the tire manufacturer wishes to investigate the tread life of its tires. A sample of 10 tires, so what's the degrees of freedom if we have 10 tires? The degrees of freedom is 9. Okay, so degrees of freedom equals 9. Okay, tires driven 50,000 miles revealed that a sample mean of 0.32 inches. Okay, so we've got 0.32 inches is x bar of tread remaining with a standard deviation of 0.9. Now remember, with a population standard deviation, it's sigma, but here we are using s. Okay, so we have, right down here, 0.32 plus or minus. We're going to look at the t really quick, but then we've got the standard deviation. The standard deviation is 0.09, and the square root of n, so we've got the square root of 10. Okay? So let's take a look. We've got the degrees of freedom that we need to calculate, which is 9, and I'm going to pull over this chart. So once again, we find the degrees of freedom, 9, and we find the cross-section of 95, the confidence interval of 95, and it's 2.62. So 9, 95, 2.262. Okay, plus or minus 2.262 multiplied by 0.09 divided by the square root of 10. So we come over here, equals 0.32 plus or minus 0.04. Now what is this 0.04 called? This 0.04 is called the margin of error. Margin of error. And I'm going to keep on asking you guys about that over and over and over again. So the margin of error. The endpoint of the confidence intervals is 2.56 and 3.84, and the margin of error is 0.64. So the manufacturer is 95% confident that the mean remaining tread depth is between 0.256 and 0.384 inches. Because the value 0.3 is in the interval, it is possible that the mean of the population is 0.3. Okay, so that right there is levels of confidence utilizing the t distribution.